chapter. I say that about all the chapters, though, don't I? All right, Chemistry 3111. This is chapter 17, which deals with aromatic compounds. And if you go back to Organic Chemistry 1, you remember that when you learn functional groups, you learn that this is an aryl group or an arene. Sometimes we call it an aryl. Sometimes we call it an arene, right? And that molecule is called benzene. Everybody knows what benzene is by now. And we just call that an aromatic ring. Well, I'm here to tell you that there's lots of things that have other atoms in them that are aromatic. Like, for example, pyridine is an aromatic compound. If I have, let's say, something like this, a little bit more interesting, if I have a heterocycle like this where I have a nitrogen and an oxygen in the ring, that's an aromatic compound. What's another example of something? Even if you have something with 3 heteroatoms in the ring, okay? This is also an aromatic compound that I'm drawing out here. So, aromatic compounds doesn't necessarily mean that the compound is benzene or some derivative of benzene. Another interesting thing about aromatic compounds is, just the name aromatic would imply that they have some kind of fragrant odor. And the book goes into a little bit of detail about this, but the whole idea of aromatic compounds, the first truly aromatic compounds that were isolated did come from tree balsams and saps or resins, and they probably did have fragrant odors. However, since then, we've discovered many more aromatic compounds that either have no odor at all, or maybe they have a foul odor. So aromatic, what it means is something that's stable. Okay, it means there's some kind of inherent stability in the ring. So we'll put here. Let's just put stability. Okay, there's something to do with stability when we're looking at aromatic compounds, because we can even look at ions and consider them aromatic. Say, for example, I have a 5-membered ring with 2 pi bonds and a carbanion. That's an aromatic compound. I can even have an aromatic compound where I have a positive charge in the ring. If I have a 7-membered ring like this, and if I have 3 pi bonds and a carbocation like that, that's also aromatic. So we can even have an aromatic ion. So something to think about before we really get into the nuts and bolts. And if you have questions about, how would I know that this is aromatic? And how would I know that these ions are aromatic? Well, these are questions that we're going to answer in this chapter. All right, well, let's take a look here. Aromatic compounds or arenes include benzene and the derivatives of benzene. For example, if I just put a methyl group on a benzene, right, and I have a CH3 group here, that's called a toluene molecule. If I have 2 methyl groups and they're ortho to each other, I call that orthoxylene. If I have them meta to each other, so if I have them in the 1,3 position, this is called metaxylene. And you can guess where I'm going with this. If they're 1,4 substituted, you probably guessed, I'll try to be consistent here, then we call that paraxylene. So orthoxylene, metaxylene, and paraxylene. Sometimes you just get a bottle that has all 3 of these mixed together, and they just call it xylenes, okay? Because they all have similar boiling points. But again, the word aromatic denotes the fact that the original aromatic compounds that were isolated were fragrant and probably did have good, had some kind of nice odor to them. However, most aromatic compounds are in fact odorless, and there's some like pyridine, for example. Pyridine, and I know you all know the structure of pyridine. I drew it on the first slide. If you take a benzene and you just substitute one of the carbons for nitrogen, this is pyridine. Well, I can tell you from plenty of firsthand experience that pyridine has a very foul odor. Okay, it actually hurts my nose if I breathe it in. It has a horrible, horrible smell. Do not like the odor of pyridine at all. Something that you might find interesting about aromatic rings or aromatic compounds is that aromatic rings are a very common feature found in drugs. And something that we could do someday in class, if you remind me, is to look at the list of the top 200 marketed drugs by profit or, by prescription. And if you look at a lot of these drugs, and the drugs have an IUPAC name, and they also have a trade name, and they also have a generic name, that many common drugs or many drugs have aromatic rings in them. Now, hopefully nobody in our class is taking Lipitor. That's for people who have, cardiovascular disease. It's like a blood thinner. So Lipitor, you can see it's got 3 aromatic rings in it. Here we have Zyprexia. So Zyprexia, which has an aromatic ring. What's one that everybody would know? Something like Prilosec, okay, or Losec, right? You can buy Losec or omeprazole down at the Costco. They sell it by nearly the metric ton, right? And so it's basically not an antacid, but it's a proton pump inhibitor that will help you if you have acid reflux. The same thing with Prevacid here, but you see that there's some commonalities between these two compounds. I mean, if you look at just this part of the drug here, right? If you just look at this part, it's identical over here pretty much, you know? You just look at this part. We call that the chemotype anyhow, and then the rest is kind of different between the two of them. What else? Plavix is over here. When I was working for BMS, they had just started marketing Plavix or started selling it the year before. Anyhow, so these are drugs that make billions of dollars in profits, but anyhow, and you see that they all have aromatic rings in them. Another place you'd find aromatic ring is in coal. If anybody here has ever seen an old coal-fired stove before, or maybe you've used charcoal in a barbecue before, and here's, you know, just a shovel with some coal on it right down here at the bottom. What's coal made of? Well, coal is just like a haphazard arrangement of aromatic rings with non-aromatic portions that bind it together. I mean, where does coal come from? Coal comes from organic material that died, you know, millions of years ago and was put under intense heat and pressure to form the coal that you see here. And of course, they have all the aromatic portions highlighted in orange, and then the non-aromatic portions highlighted in green. So we see aromatic rings in coal as well. So there's a, you know, very common place that you would find coal. In fact, the textbook says something like there's enough coal in the United States to keep it running for the next 150 or 200 years or something like that. So there's a lot of energy available from coal. And I think that a good chunk of Americans get their electricity from coal, even if they don't want to admit it or they don't know it. Anyhow, what about benzene, right? We spend a lot of time talking about benzene. Now, again, every student needs to know the structure of benzene, which is just a 6-membered ring with pi bonds and sigma bonds that alternate. So, the pi, right? The single bond and double bond that alternate around the ring like that. Well, what if I put a substituent on a benzene ring, right? Some of them have common names, and we're going to look at those on the next slide. For example, I told you that if you put a methyl group, that's called toluene, right? And there are others that we'll look at in a second. But some monosubstituted benzenes do not have common names. Some of them just don't have common names. Say, for example, if you put a chlorine on a benzene ring, it's called chlorobenzene, right? If you put a nitro group on a benzene, nitrobenzene. If you have ethyl, you know, if you have an ethyl group on there, you call that ethylbenzene. Okay, so there's all kinds of different, just ways that you can name these molecules. Not all kinds of different ways, but what I mean is all kinds of different molecules. You just list the substituent first, and then you put benzene after it. But there are some common monosubstituted benzene derivatives that you have to have committed to memory. Okay, everybody who's hearing the sound of my voice, whether they're in live class right now or if they're watching this video at home, okay, you've got to know all of these organic molecules by their common name, right? We don't call this methylbenzene, we call it toluene. We don't call this hydroxybenzene, maybe Wikipedia does, but we call it phenol. We don't call this methoxybenzene, we call it anisole. So this is one that you probably haven't seen before, is anisole, right? A pyridine is when the nitrogen is inside the ring, but when you have a primary amine attached directly to an aromatic ring, this is called aniline or aniline. The next one is benzoic acid. I'm going to assume that you all know a benzoic acid because that is very commonly recrystallized in chemistry 3102 at UCCS. The next one is benzaldehyde. So if I put an aldehyde right on a benzene ring, I get benzaldehyde. This one is probably, this one and styrene are probably the least intuitive of all of them for students. So this one is called, if you put a methyl ketone, right? This is a methyl, this is a ketone. So if this together, we call it a methyl ketone. When you put that on an aromatic ring, we call that acetophenone. So acetophenone shows up all the time in organic chemistry. Could be a good electrophile for a Grignard reaction, let's say. And then this one here is styrene. And I know you've all heard of polystyrene, which is what the original styrofoam was. It was just a polymer of styrene. Now there's different additives that are put in the polystyrene. But anyhow, when you have just an ethylene group attached to an aromatic ring, that is a styrene. So again, you need to be able to memorize all of these because some di-substituted and tri and whatever substituted aromatic rings, we will look for these common names. Okay, we will look for these molecules as part of an overall structure. And so it's very handy. And when I say handy, I'm sounding like my father. What I mean is that you need to know the names of these molecules. All right, and they're common, right? They're just so common in organic chemistry that all organic chemists need to know their names. Things like benzoic acid, you know, we probably saw that in spectroscopy, but something like phenol, for example, I know where you would have seen that. You would have seen it in chapter 3 of Chemistry 3101 when we talked about pKa's, because the pK of phenol is actually in the table, and the pK of phenol is around 10. So kind of interesting there. Well, what if we're dealing with a group that is bigger than our benzene ring, right? There's only 6 carbons in benzene. So if benzene is a substituent on something that's got more than 6 carbons, we call it a phenyl. Okay, so when benzene, or when the aromatic ring is a parent, we call it a benzene. And when it's like an R group, right? You guys know what a methyl group is, right? You all know what an ethyl group is. Well, when a benzene ring is considered like a substituent, in that case, it's not called benzene, it's called a phenyl. Okay, it's like its name changes when its identity changes. So here we have one phenylheptane. Why? Because the parent chain has what? 1, 2, 3, 4, 5, 6, 7. 7 carbons is greater than 6 carbons, and therefore this is the parent over here. So now the benzene ring is not the parent, it is a substituent. So we call it 1-phenylheptane. Now, phenyl as a substituent, when you have a lot of them, can get a little cumbersome to write down phenyl and to draw all these 6-membered rings. And so let's say you had this molecule here, tetraphenylcyclopentadienone. We got 4 phenols here. So we can shorten phenyl with a pH for phenyl, or sometimes we use the Greek symbol phi. I mean, the whole phi thing, I mean, it's always been in the textbook ever since I've taught this class, but that's something I haven't even thought about ever using with my students. It's not that common anymore. I mean, if you look around the internet, there's probably somebody who uses it here and there, but most of the time with my students, I use pH like that. Not to be, you know, which is the same thing as pH. Not to be confused with pH, right? The puissance d'hydrogène, okay, which is the power of hydrogen. That's something else, okay? pH value. Anyhow, let's take a look here. The common name for a dimethylbenzene, as I told you, is xylene, and you need to know ortho, meta, para, and what those substitutions mean. So if you have 1-2 substitution, right, here we have 1 and 2, that's called ortho. When we have 1-3 substitution, it's called meta. And when we have 1-4 substitution, that is called para. So you need to know the difference between ortho, meta, and para in terms of substitution on a benzene ring. Now, something I want to point out to you before we get into, you know, using ortho and meta para. Okay, if you're not awake, or if you're only paying like half attention, you're like looking at something else, okay, you're like reading Twitter while you're listening to me, which I hope you're not doing. Ortho, meta, and para can only be used for di-substituted benzene rings. Once you have 3 substituents or more, or if you only have 1 substituent, you cannot use ortho, meta, para. I repeat, ortho, meta, para is only used for di-substituted benzenes. That's it. Di-substituted. What does di mean? 2. Okay? If you have more or less than 2, you cannot break out the ortho, meta, para party. All right? So let's say we have these 3 molecules here. How would we name these? Well, what you would do is you would look for one of those common parents that I told you had to memorize, right? Right here inside this blue loop that I'm making, we have an anisole. Anisole. And what we do is we assume that the carbon that has the methoxy group on it, okay, in our anisole, we're always going to assign that number 1. And so we seek to give the nitro the lowest possible number. So this would be 2-nitroanisole, or you could call it ortho-nitroanisole. Remember, the ortho means that the groups are 1-2 disubstituted. All right, the next one. You see the parent that we have in here is toluene, right? Methylbenzene is also called toluene. So we could call this 3-bromotoluene because we assume the methyl group from the toluene is 1, 2, 3, or you could call it metabromotoluene. The next one has a benzaldehyde in it. So we have a benzaldehyde molecule here. Again, where the aldehyde group is, we consider that carbon 1. We could go counterclockwise either way here, and we're going to end up with 4-chlorobenzaldehyde or para-chlorobenzaldehyde. Okay, I have a joke for you, okay? It's organic chemistry humor. Somebody in the class, I'm sure, has heard it before, but I'll just share it with you here. Let's say we call this, could anybody tell me how you would name this compound? We got 2 PhDs here in the 1-2 position. What would you call that? Since it's a PhD, which represents a doctorate, and they're 1-2 substituted, we would call this orthodox. You would say that's orthodox. And then, of course, if you have them arranged like this, and this is, again, just a joke. I'm just being silly with you guys. This is called paradox, okay? So there's some organic chemistry humor that you can share with your friends who are taking organic chemistry. Maybe, I don't know, anyhow. It's just something kind of silly there. So again, how do we name a benzene derivative? We identify the parent, and that's why we need to know the names of things like styrene, acetophenone, anisole, aniline, phenol, toluene, etc. Benzaldehyde, right? Then you identify and name the substituents. You number the parent chain, assign a locant to each substituent. Here's an important rule that I didn't mention today, not yet. You give the first substituent the lowest possible number. Okay, you don't start tallying them up or anything like that. You just give the first substituent the lowest number you can, then to hell with the rest, give them whatever number they get. Number 4, list the substituents before the name in alphabetical order. We ignore prefixes except iso, cyclo, and neo when ordering alphabetically. There you go. Well, let's take a look here. It says identify the parent chain. Well, this one here, you can see I kind of gave it away because I highlighted it in red. Right, we have a phenol, and whatever the parent is, which is, again, highlighted in red, the carbon that has the substituent on it, we call that carbon number 1. So we could go clockwise or counterclockwise here. It doesn't matter. 2, 3, 4, 5, 6. So we have a 3,5-dibromo. Dibromo. And then we have a phenol. So if we put all that together, we get 3,3-dibromo phenol. And that's it. There you go, 3,3-dibromophenol. All right, nothing to it. Well, with that in mind, let's see if we can name the following molecules. Maybe I shouldn't have done the highlighting here in red. Kind of gives away some of the answer, but we're learning, so let's give it a try. You know what? Let's name the following molecules. So these are all di-substituted benzenes. Could anybody, what did I put? Oh, 3. I was testing you to make sure somebody was awake. It's 3, 5. There you go, 3, 5. Good, 3,5-dibromophenol. All right, let's see. If we want to name these molecules, let's call this first one, we'll call it A, call this one B, and we'll call this one C. If I want to name A, could anybody tell me what the parent in A would be? Could anybody tell me what the parent in A would be? Absolutely. Thanks, Jisoo. It's benzaldehyde, right? So what she's saying is right here, I have a benzaldehyde. There you go. And then I have a chloro over here. So I go 1, 2, 3, 4. And so we can call this molecule 4-chloro benzaldehyde, or I could call it para. And you can just use the letter P, or you can write it out. Para-chloro benzaldehyde, aldehyde, like that. So again, if we have ortho, you can just call that O. If you have meta, you can just call that M. And if you have para, you just call that P, like that. Can anybody give me a name for the second one?
Is it 2-bromotoluene?
Close, yeah, very close.
Yeah.
So, David, what locant would I give to the methyl, right? You don't write it down, but this is group number 1. So if this is group number 1, what locant do I give to the bromine in this case?
That's 3, yeah.
There you go, exactly. Exactly. So this is some kind of toluene. We got that established right away. And this would either have to be 3-bromotoluene, because where the substituent is, where that methyl group, I assume that's 1, 2, and then 3 over here. Or, as somebody else, oh, I guess nobody wrote it, but you could also call this meta-bromotoluene. Same thing. Okay, and the last one. Could anybody tell me what the parent is in the last one? One of the ones that's a little tougher to memorize, I think, because it probably doesn't even show up until this chapter. Yeah, exactly. It's anisole. Yep, anisole. And this is the anisole portion here. All right, so this is 1, this is 2. So we could call this 2-nitro-anisole, or we could call it ortho-nitro-anisole. All right, so these are all di-substituted, in case you didn't notice. So all are di-substituted, and that's why we can use the ortho meta para in these particular examples. Well, let's take a look at some other ones. So I'm going to give you a couple seconds to think about these, because the third one is not di-substituted. Give you about a minute to try and solve all these. And if anybody has any answers, feel free to just type them in. All right, does anybody have a name? Oh, let me see here. Go. Yes, meta-isopropyl benzaldehyde. Yeah, I would definitely take that. Yep, so for the first one, somebody put, well, there's a benzaldehyde here. And if I go 1, 2, 3, so that's meta. So somebody said that somebody was Skylar, meta-isopropyl benzaldehyde. Yes, absolutely. Or you could call it 3-isopropyl benzaldehyde. That works too. The next one, we've got a toluene in here, don't we? Yes, we've got a toluene. So you could call that 1, 2. So we could call this 2-bromotoluene. Or you can call it ortho-bromotoluene. What about the last one? What's the parent in the last one? Yes, absolutely. It's a phenol, right? We've got a phenol right here. Now remember, the rule is that we want to number it in such a way that we give the first substituent the lowest possible number. So 1, 2, 3, 4, right? If we had gone the other way, instead of having a 2, we'd have 1, 2, 3, 4. 4 would be the first substituent. Well, 2 is lower than 4, right? 2 is less than a number 4. So we have 2, 3, 4. So we have 2,4-dinitrophenol. So 2,4-dinitro. Phenol. Like that. And we can't use ortho-meta-para here because this is tri-substituted. So write this here. Cannot use ortho-meta-para since tri-substituted. All right, here we go. Let's move on from there. Let's see if we can draw some compounds. I'll give you a second to try and draw 2,6-dibromo-4-chloroanisole and meta-nitrophenol. I'll give you a second. These ones don't take that long usually. I don't know if you're able to post your drawing up in the chat, but if you could, I don't know how easy that is to do. It might be too time consuming. All right, let's take a look at the first one. We got 2,6-dibromo-4-chloroanisole. We'll start by drawing anisole, which is an aromatic ring or a benzene ring with a methoxy group on it. Like this. If we call this number 1, 2, 3, 4, 5, 6. The carbons 2 and 6, we need bromos. So let's erase those and we'll put a bromo in here and a bromo in here. And then at carbon 4, we need a chloro. So let's throw that in here. And there you have it, my friend. There's your first tetra-substituted benzene derivative. Next one is meta-nitrophenol. So we'll start by putting our phenol here. And if it's meta, well, it's 1,3 substituted. So we have a nitro group over here like that. All right. Well, that's a little bit of nomenclature of benzene derivatives. Again, I think the hardest part of benzene derivative nomenclature is memorizing those 8 benzene derivatives that you're expected to know the common names of. Section 17.3 deals with the structure of benzene. I mean, how many times have you seen this structure in organic chemistry? Well, what's interesting about the structure of benzene is that chemists knew the molecular formula for a long time. They knew that it was C6H6. However, they did not know the structure. And if you look up the history of benzene, and I'm not going to go over the history lesson right now, but there are some really interesting, very interesting molecules that were proposed for the structure of benzene. And so it wasn't until 1866 that Auguste Kekulé proposed that a benzene ring is actually comprised of a ring which has the alternating double and single bonds. Now, he had the famous dream about the snake eating itself by the tail, and that's kind of what led him to his discovery. I'm not sure how much truth there is in that, but there was even, I think Kekulé is Dutch, maybe, and there was even a commemorative stamp that had the snake consuming itself by the tail on the stamp. So there might be some truth to it anyhow. But what he had wrong is that he thought that this was an equilibrium process, right? The alternate or the exchange of the double and single bonds. He said that's in equilibrium, right? This is an equilibrium arrow set here, but we know it is not an equilibrium, is it? We know that it is in fact a resonance. These are resonance structures, okay? And so this is the correct arrow that we use for resonance. And the fact that we use these square brackets tells us that neither of these actually represent the molecule. These are both representations that help us understand the resonance hybrid, right? Because we know that since we have a continuously overlapping system of p orbitals, because each one of the carbons in benzene is sp2 hybridized, that all of the electrons in the p orbitals are delocalized across the entire ring. And so sometimes we draw the benzene ring as a hexagon with a circle in the middle, and we use that to avoid drawing resonance structures. Now, some people really like to use this. I don't like to use it a whole lot, and maybe it's just because I'm a chemistry teacher now. And what you're going to find is that if you start trying to draw this all the time now, once you get into chapter 18 and you actually need to draw mechanisms wherein you use the double bonds in a benzene ring, then the circle isn't really helpful for you. Okay, it doesn't really help you out a whole lot. Well, what about the stability of benzene? If you remember at the very beginning of today's lecture, on the title slide, what I actually talked to you about was, what does aromatic mean? You know, it doesn't mean fragrant. It means that it's remarkably stable. So there's an inherent stability to aromatic rings. Now, based off of what you learned in the alkenes chapter of Organic Chemistry 1, you all learned this reaction where we take an alkene. If we were to treat that with bromine, let's say, in a chlorinated solvent, maybe dichloromethane, CH2Cl2, that would make a good solvent. You end up with an anti-addition of bromines to make this trans 1,2-dibromocyclohexane. Okay, so that's just a reaction of what? An alkene, and it's undergoing bromination or an addition reaction. You take benzene and you subject it to the exact same reaction conditions. Let's say you try same solvent and everything, and nothing will happen. Okay, and you might be thinking, well, come on, you've got 3 sweet pi bonds in here. Shouldn't those things react? Theoretically, yes, but we find out that they don't. Okay, and there's a good reason for that. In fact, if you compare the heats of hydrogenation of cyclohexene, so here's cyclohexene, it's got 1 carbon-carbon double bond in the ring. Okay, we find that 120 kilojoules per mole of energy is released when you hydrogenate that molecule. If you have 1,3-cyclohexadiene, you subject that to hydrogenation, you release 232 kilojoules per mole of energy, right? It's not double, but it's close to double. So you think, okay, well, if I add a third double bond and I make this theoretical molecule, which would be called 1,3,5-cyclohexatriene, and you hydrogenate that, you would think it should be around 360 kilojoules per mole. But what you actually find is that when you hydrogenate benzene, you only release 208 kilojoules per mole. It's even more stable than this molecule. What does that tell you? Right? You have all this gained stability that you wouldn't think of intuitively. So again, what does that tell us? That tells us that when we hydrogenate benzene, since less energy is released, what does that tell us? It tells us that it's more stable than we would anticipate, right? There's an inherent stability in benzene that we could not anticipate. And so where does that stability come from? Well, don't get scared, but we have to talk about molecular orbitals for a couple of seconds in order for us to understand the stability of benzene. But I'm going to explain it as simply as I can. Right, if you think about a benzene ring, each carbon in a benzene ring is sp2 hybridized. That means that each one of these carbons, since they're all sp2 hybridized, they've all got an unhybridized p orbital, don't they? Right, sp2, but that means they all have an unhybridized p orbital on them. Okay, now it's better represented here than I could ever draw. But here you see the p orbital. This is just a p orbital, and there is an unhybridized, that's what the p orbital is. It's not a hybrid orbital. Okay, there's an unhybridized p orbital on each one of the carbons in the aromatic ring, right? Because every carbon is sp2 hybridized. Okay, what happens is, since we have 6 atomic orbitals, remember that the number of atomic orbitals is equal to the number of molecular orbitals that's formed when we look at molecular orbital theory. Well, if I have 6 atomic orbitals, I'm going to have 6 molecular orbitals. Now, to write down all of the 6 molecular orbitals involves quite complex mathematics, which we don't really concern ourselves with in Chemistry 3101. But when you see those 6 molecular orbitals arranged in terms of their relative energies, we end up with something like what is shown here, where we have 3 bonding molecular orbitals, and we have 3 anti-bonding molecular orbitals. You can see that they're labeled Psi1, Psi2, Psi3, Psi4, Psi5, right? Psi6, okay? Now remember, as you go from Psi1, it has 0 nodes, no nodes, to Psi1, which has, from Psi1, which has 0, to Psi2, which has 1 node, and then to Psi3, which has 2 nodes, and then you keep working your way up, right? All the way up to Psi6, which has 5 nodes. Now, again, that's neither here nor there a whole lot. But since each one of those p orbitals has 1 electron in it, and each molecular orbital can hold a total of 2 electrons, where do all the electrons end up? Well, if we follow Hund's rule, the Aufbau principle, okay, in the Pauli exclusion principle, what we see is that all of the electrons that were in each of the p orbitals, where do they all end up? They end up in Psi1, Psi2, Psi3. And if you're like, okay, great, they end up in those. More importantly, they all end up in bonding molecular orbitals. So none of them end up in these unstable anti-bonding molecular orbitals. And that's what's so important. Okay, that's why benzene is so stable, because every electron from the p orbitals, they're all in bonding molecular orbitals. All right, so there you go. The shape of those MOs, again, involves high-level mathematical calculations. You don't have to worry about that in Chemistry 3101, okay? What you've got to understand is that those 6 pi electrons, right, from the 3 double bonds, okay, if there's 3 double bonds and each one has 2 pi electrons in it, 1, 2, 3, 4, 5, 6. What you've got to understand is they all end up in bonding molecular orbitals, which you can see are lower in energy, and that's what accounts for the inherent stability of a benzene molecule, or an aromatic ring, so to speak. Well, with all that information in mind, you know, you take a look at this molecule and you say, well, it's kind of interesting here. I have, you know, pi bond here, and then I have a sigma. Then I have a pi, then I have a sigma. Then I have a pi, you know, then I have a sigma. They alternate like that. So it might be a knee-jerk reaction to think, well, anytime I have a cyclic molecule, and if I have the pi and sigma bonds, or double and single bonds alternating, because these 2 molecules both fit that bill, don't they? You might think, well, they should be really stable. Cyclobutadiene, look, we have single, double, single, double. Okay, it's just a 4-membered ring. Here we have an 8-membered ring, cyclooctatetraene, same thing, you know, double, single, double. And you might think, hey, those should have aromatic stability, shouldn't they? However, what happens with these molecules? Check this out. Do you remember how I told you if you took benzene and you treated it with bromine, nothing happened? Well, if you take benzene and you put, cyclooctatetraene, this guy here, and you put it in bromine, reacts, boom, no problem. You end up with the anti-addition, you get the enantiomer. So what does that tell you? It tells you this thing doesn't have aromatic stability. What about cyclobutadiene? This molecule is so stinking reactive that if you put it next to another molecule of cyclobutadiene, it reacts to form this 3-membered ring, which undergoes a sigmatropic rearrangement and rearranges to form cyclooctatetraene. So you're like, well, that's not very useful or anything. What's the take-home message of this slide? Is that just because you have a fully conjugated ring, it doesn't mean it's aromatic, right? Neither of these are aromatic. This molecule isn't aromatic, obviously, because it reacts with itself. And this molecule isn't aromatic because it reacts with bromine like nothing. Well, why aren't they aromatic? Is there a rule that I could follow, Mr. Dion, for me to know why these aren't aromatic and why benzene is aromatic? Yes, there is. We're going to get to that in a second. Let's talk a little bit more about this, though. It says, in order for a compound to be treated as aromatic, like benzene, here's the answer. It's got to have a fully conjugated ring with overlapping p orbitals. Okay? And it's got to meet a rule that we call Huckels' rule. Now, what's Huckels' rule? Huckels' rule is that we have an odd number of electron pairs. Okay, what's an odd number? 3, 5, 7, 9, 11. right? So we've got to have an odd number of electron pairs. Put another way, okay, so that's what the word or means. Put another way, it has to have 4n plus 2 total pi electrons, where n is 0, 1, 2, 3, 4. Let me show you how this works. If we go back here and we look at benzene, okay? Let me redraw the molecule here. This is benzene. How many pairs of pi electrons do we have? We have, I can clean that up a little bit. How many pairs of pi electrons do we have? Look carefully. This is a pair of pi electrons. This is a pair of pi electrons. And this is a pair of pi electrons. So what do we have? We have 3 pairs of pi electrons. 3 is an odd number. 3 is an odd number. Therefore, this is going to be aromatic. All right, that explains why benzene is aromatic. Let's go over here. I have, look, 1, 2 pairs of pi electrons. 2 isn't an odd number. Therefore, that's not going to be aromatic. Over here in cyclooctatetrene, I have 1, 2, 3, 4. 4 isn't an odd number, so it's not going to be aromatic. Let's take a look at the next requirement. A fully conjugated ring with overlapping p orbitals. Now, both of these molecules meet that requirement, don't they? Right? Because every carbon here and every carbon here is all sp2 hybridized. But again, they don't meet Huckel's rule. So I showed you the odd number of electron pairs treatment. So odd number of electron pairs. I think that's easy. The easier one, an odd number of electron pairs. I should have just highlighted up to here. The 4 plus 2, 4n plus 2 rule, excuse me, where n is an integer, 0, 1, 2, 3, 4, 5, 6, 7, whatever. Okay. Let's take a look. Let's go back to the benzene. If I have 4n plus 2, where n is equal to 0, 1, 2, 3. Well, how many total pi electrons do I have in this molecule? Let me show you. I have a total of 1, 2, 3, 4, 5, 6. So if I have n is equal to 1, I have 4 times 1, which is 4 plus 2, is 6. Therefore, 6 pi electrons, 6 pi electrons, therefore a Huckel with the umlaut, Huckel number. Okay, so it works both ways. Whereas here, this is not, doesn't fit the 4n plus 2. Right, if you go 4n plus 2, when n is equal to 0, then I have 4 times 0, which is 0 plus 2. So then I'd have 2. Well, neither of those have 2. Then if I go to n is equal to 1, then I have 6 pi electrons. Neither of these have 6. Then I go to n is equal to 2. 2 times 4 is 8, plus 2 is 10. And you can see that we skipped the 4 and we skipped the 8. So that means that neither of these are going to be aromatic. Again, they don't have a Huckel number of electrons. They don't have an odd number of electron pairs, even though both of these have a continuously overlapping system of p orbitals. All right? So you got to meet all the requirements in order to be aromatic. All right. We can also explain Huckel's rule, right, which is the 4n plus 2 rule. Same thing, okay? We can also explain Huckel's rule using molecular orbital theory. Now, again, don't turn me off and don't say, oh, dang it. Molecular orbitals again, those are complicated. Well, I'm going to show you a shortcut, okay? It says, consider the molecular orbitals for cyclobutadiene. Now, we said that this isn't an aromatic compound, didn't we? Right? Because it didn't have a Huckel number of electrons. It doesn't have an odd number of electron pairs, even though it does have a continuously overlapping system of p orbitals. But if we write out all the molecular orbitals, okay, we have 4 p orbitals, and each one of them has an electron in it, right? Each one of them has an unpaired electron. Well, when I read out the molecular orbitals here, they look a little different, right? The lowest energy molecular orbitals are the bonding. The highest are the anti-bonding, but the ones that are right dead center, okay, right dead center, those are called non-bonding. Now, since I end up with a pair of electrons in bonding orbitals, or in a bonding orbital, and then I have 2 unpaired electrons in non-bonding orbitals, That's why this thing is so reactive, because it's got basically unpaired electrons. It's like it has unpaired electrons, okay? It doesn't have what the book calls a closed shell electron configuration, which is where all of the electrons are in bonding molecular orbitals, and therefore it's unstable. And then we would say it's anti-aromatic. Okay, it's not aromatic, it's anti-aromatic. Now hold the phone. Before we just start throwing the book at this thing, let's take a look at cyclooctatetraene. And I'm going to talk more about this anti-aromatic thing in a few minutes. Okay? If we look at our molecule of cyclooctatetraene and we write down the molecular orbitals for it, we end up with 3 that are bonding molecular orbitals, 3 that are anti-bonding, and then we end up with 2 that are dead center. Look, if each one of these 4 p orbitals has an unpaired electron, I'll just write them alternatingly. Okay? Then we have a total of 4 electrons. 6 of them can go in bonding molecular orbitals, but now I've got 2 unpaired ones, right? Remember Hunt's rule or the bus rule? We end up with 2 unpaired electrons in non-bonding molecular orbitals. And so we would think that this is anti-aromatic. Well, I don't have a lot written down in my notes for this chapter, but if there's one thing I scribbled down is, what is an anti-aromatic compound? And I encourage you to actually Google this. It's the only time I'll ever tell you to do something like this in an organic chemistry class. Why? Because I don't think our book goes into enough detail. It's the only time where I feel like he could have gone into a little more detail. Okay? But before I show you some anti-aromatic compounds, some true anti-aromatic compounds, I want to point something out to you, which is this. Okay? Listen to me very carefully. You see that the word anti-aromatic showed up on this slide, right, for this molecule, and then the word anti-aromatic shows up here for this molecule. Well, I'm here to tell you, my friends, that neither of these molecules are actually anti-aromatic. You're like, Mr. Dion, you're disagreeing with your own dang slides. What are you doing? Hold on. Here's the bottom line, you guys. If a molecule is anti-aromatic, or if it could be considered anti-aromatic, like cyclobutadiene and cyclooctatetraene, here's the answer. It will do everything in its power, to its ability, to avoid being anti-aromatic, because anti-aromatic compounds are so unstable. So what cyclobutadiene actually does is it adopts a rectangular shape. Now, so it does something like this. Okay, it kind of flexes back and forth between this and this, okay, where it stretches back and forth, okay? And the reason it does that is that way it avoids the continuous overlap of the p orbitals, right? Because if this bond gets stretched out enough, or if this bond gets stretched out enough, you can avoid the overlap of those p orbitals. This is covered in our book, okay? So I'm not just throwing it out there for your own personal edification. It is in our book. It's in the section that we're in right now, which is section 17.4. It does show the cyclobutadiene. It does show it stretching. Now, it says right here, it says cyclobutadiene, and I'm reading from the book, can alleviate some of this instability by adopting a rectangular shape that I have drawn here, in which the compound functions as 2 isolated pi bonds, okay, rather than a diradical, which we would have because we have 2 unpaired electrons. There is strong evidence that cyclobutadiene rapidly equilibrates between the 2 rectangular forms. Now, I don't have them drawn exactly the way they are in the book. They do it like this. So they have it like this 1 second, and then they have it like this. That's neither here nor there, really. The whole idea is that it adopts the rectangular shape to avoid the overlap of orbitals, so that it doesn't become anti-aromatic, it becomes non-aromatic. Non-aromatic. Okay? Now, what can this guy do? The cyclooctatetraene, what can it do to avoid becoming or being anti-aromatic? Well, it does something very different. It adopts a tub shape, and you can see how this looks like a tub, right? You could picture yourself in here with a glass of wine, mystery novel in this hand, right? And then you're sitting in the tub, right? You're sitting in the tub like that, okay? Because you're not thinking about organic chemistry for a couple of seconds, right? So it adopts this tub shape, okay? And what that does is the same thing, is that it prevents the continuous overlap of the p orbitals. It breaks up the overlap, okay? And so since the conjugation doesn't really extend around the entire ring, it's not anti-aromatic, it's non-aromatic. Okay? Remember, a molecule will do anything it can to avoid being anti-aromatic. So, student of mine, a number of years ago, and I'm going to write it down. Where would I find some space? Okay, I'll write it up here. Student of mine asked me a number of years ago, like, well, Mr. Dion, I started researching, and there aren't that many anti-aromatic compounds. So depending on where you look, you'll see that anti-aromatic compounds, okay, are things like a three-membered ring with a double bond and an oxygen. That's anti-aromatic. Same thing here. If I have a three-membered ring with a double bond and a nitrogen in it, or if I have a three-membered ring with a sulfur in it, these are all anti-aromatic. They're so unstable. Another example of an anti-aromatic compound would be if I have this bicyclic system, and if I have double bonds here and here and here. Another example is the cyclopentadienyl cation, like that. That's anti-aromatic. Another one that I have written down, I'm kind of running out of space here, aren't I? Is this guy. If you have a six-membered ring, and then a four-membered ring, and then another six-membered ring, and you have your double bonds like this, and like this, and like this, okay? These are examples of anti-aromatic compounds, and again, cyclobutadiene, some places will say that it's anti-aromatic, but the author of our book considers it non-aromatic because it does that bond stretching thing that I just told you about. So in fact, there are very few anti-aromatic compounds. And later on, when we get into practice in this chapter, and we will do some practice, that will hopefully help the concept of anti-aromatic versus non-aromatic versus aromatic to crystallize in your mind and really help you understand how to discern between anti-aromatic, aromatic, and non-aromatic. Well, let me show you something called frost circles. Now, hopefully you took the time to read this chapter before coming here today. And frost circles are a simple way, instead of using molecular orbitals in, using the complex mathematics, for us to predict the relative molecular orbital energies, and also to be able to predict whether a molecule will be aromatic or not. Okay? So this is what we do. It's a 5-step process, and it's not that difficult. The first step, you draw a circle. The second step, you inscribe a polygon. So if you have a 4-membered ring, you put a 4-membered polygon, right? You put a square. If you have a 6-membered ring, you put a hexagon inside it. And you make sure that all the vertexes touch at points along the circle, and you always have a point touching at the very bottom, okay? So let's say you had the circle, and you wanted to put a square, you would put it in like this, okay? So you'd have a point touching the very bottom, like that. Then what you do is you draw a horizontal line at each point of the intersection. So here they're doing a 7-membered ring. For our 4-membered ring, it's the exact same thing. So I'll just copy and paste this. So copy and paste. So what you do, everywhere that it touches the circle, you draw a horizontal line. So one here, one here, one here, one here, and those represent the molecular orbitals. All right? You draw a line through the center. Okay, so if we take this thing again, right, down below, they're doing it with a 7-membered ring. Up top, we're doing it with a 4-membered ring. You draw a line right through the middle. I'll use the green pen this time. Draw a line right through the middle, like that. And then anything that's below the line is considered a bonding molecular orbital. Okay. Anything above the line is considered an anti-bonding molecular orbital. And anything that's right on the line, as in my example here, so I'll just delete some of this spinach. Okay, I'll delete all this like that. Okay, anything that's right in the middle is considered non-bonding. So this would be an anti-bonding. So this is anti-bonding. This would be a bonding. And then down here, we are in the middle, we have non-bonding molecular orbitals. You can see there's no non-bonding molecular orbitals here, okay, in this particular example. So that's what a frost circle is. Once you've got that done, you fill it up with electrons. Okay, so frost circles help us to understand the Huckel rule, because when n is equal to 0, we have 2 electrons in bonding molecular orbitals. When n is equal to 1, we have 6 electrons in bonding molecular orbitals. When n is equal to 2, we have 10 electrons in bonding molecular orbitals. Well, looky. If you take 2 and divide it by 2, what do you get? 1. So if you have 1 bonding molecular orbital and it's full, it's aromatic. If you take 6 and you divide it by 2, what do you get? 3. Look at here. If you have 3 bonding molecular orbitals, 3 bonding molecular orbitals, 3 bonding molecular orbitals, 3 bonding molecular orbitals, and they're all full, you're aromatic. Okay? If you take 10 and you divide it by 2, what do you get? 5. If you have 5 bonding molecular orbitals, or you have 5 bonding molecular orbitals here, what do you get? You get something that's completely aromatic. And there you have it, my friend. That's all there is to it. But the Frost circle, which was developed by Arthur Frost, just gives us another rationale for the Huckel rule. Notice very carefully that the number of bonding molecular orbitals is always an odd number, right? It goes from 1 to 3 to 5. Okay, it's always an odd number of electron pairs. So I love it when a story comes together. All right, so here we go. Aromatic versus anti-aromatic. Aromatic compounds fulfill the 2 criteria. You've got a fully conjugated ring with overlapping p orbitals, good enough, and then it's got to have a Huckel number, okay? Huckel number of electrons. So you have an odd number of electron pairs, or you've got 4n plus 2 total pi electrons. Compound is anti-aromatic when it's a fully conjugated ring with overlapping p orbitals, but it's got an even number of electron pairs. When it fails criterion number 1, when you don't have that fully conjugated ring of overlapping p orbitals, it is considered non-aromatic. Plus, if the molecule can do anything to avoid being anti-aromatic, which most molecules will, it will be non-aromatic. This is where doing some practice comes in really, really handy. Okay? Let me give you some examples of some other aromatic compounds besides things like benzene and pyridine. But before